Okay, after the summary of the lattice types in the last lecture, in this lecture I just want to expose you to the 230 3D crystallographic space groups without actually deriving all of them, but just to show you what they look like. With your background now in deriving all of the components of all these space groups, including the two-dimensional ones, the three-dimensional point groups, and everything else, and how you can actually the lattices are generated from the two-dimensional lattices with compatible third translation vectors. You can pretty much see where they all come from. One of the confusing things in notation, which we'll cover a little bit of, but also we'll be able to show you that there is a couple of things in the international notation that point to symmetry elements and some other things that we have to derive, which we haven't done yet. So we'll motivate you with almost the end of the crystallographic section of the class by showing the 230 3D space groups, but we will then have to just finish up with a few extra lectures, and then we'll be finished with this part of the class. So what's shown here are 88. The rest of them up to 230 are our next slide, which I'll go to in a minute. But this pretty much shows everything I want to discuss anyway. Just to orient you, at the top is the simplest system where we couldn't add much symmetry, and it was a triclinic system in which all the angles and all the lengths are completely general. However, you could have a motif hanging off the lattice point with one simple symmetry element, which is a inversion center. And so there are two choices, the P1, which is the simplest of everything, or the P with an inversion center. So that hopefully gets you situated here. The Schoenflies notation is something that we don't cover in this class, but it's here. By the way, this the 230 3D space groups here have been just simply copied from the Wikipedia, and so it's available there for easy viewing anytime. And what I want to go to next is showing you, just to finish the Schoenflies notation, notice how the Schoenflies can be fairly simple because it actually doesn't describe uniquely what's in the space group. It just tells you what it's composed of. And then in the international notation, when all the symmetry elements are borne out for a particular combination of things, each one is a separate space group. And the notation itself is kind of complicated, but we'll explain a little bit of that right now and then in some following lectures. So to see how we're building up here, just to give you a general idea, of course the monoclinic was the next thing that we went to because we had said, aha, I want to add a twofold axis. That allows us to have a parallelogram in the base with twofold axes, but with translation T3, it forces us to have these rectangular sides, and that has some consequences. But the simplest one is to just build directly up from the 2D point group we had, and that would be P2, right? And so that nothing changes. The big capital P means, remember that it's a 3-dimension versus the 2-dimensional when we had P2, but because that's all we're doing, then we have a simple P2. C refers to centered, so we can have a centered lattice, you recall, and that's adding a twofold axis to the centered lattice. So that also is fairly straightforward. We'll show you that actually in the last lecture of crystallography. We'll show you these simple groups just so you get used to the patterns also derived in the international notation. However, there is something unique here. We have not been able to generate this particular thing, which we say P2 sub 1. Now, what is that? Well, it turns out that P2 sub 1 is something we have to develop now that we're in 3D. One of the few components left that we have to derive, and it's a screw axis. So that is what one of the lectures will be about, and we'll just hold that off. One of the things here is M. Again, we're adding m to the primitive lattice, and recall how you can't add it vertically to this base of a parallelogram, because clearly if I put it up on this side, this would not reflect in a symmetric way around here. However, look at this rectangular side. So I could have mirror planes coming up in this direction, for example, and they could all be on these rectangular sides, and that would be fine, right? It's just you can't have them along this. You just can't have them so that basically, if I have this base and I try to, put one in here, that's not going to flip, because when I flip, I'll have a twin plane more or less, right? So that I cannot do. So it has to be along the right rectangular edges, right? So I'd have to have it so if I'm looking down on one of those rectangular sides, right? If I'm and this is my parallelogram base, if the plane is coming out towards me here and out towards me, that'll be fine, because this is a rectangular thing, and I could have mirror planes coming out at me. And so if I insert them in nothing else, I just get PM. Now here's another notation we haven't talked about yet, which is a C, a little c. And what we're going to find out is that M is for mirror plane, but A, B, C, some other notation, N and D are all going to be, these are related to glide planes in 3D. And so you'll see them scattered through here. There's some D's, some M's, a B and an A. So when you see something like that, that's a glide plane. And now a mirror plane dominates, by the way. So if you're looking down that same axis, you can have multiple planes coming out at you. If I have a glide and a mirror, I only use the mirror. So what these notations don't tell you is that they don't tell you if there's more than one symmetry element coming out. They just give you by convention what the dominating symmetry element is. And it's the same thing for these screw axis versus twofold axis. Because I see here I have a 2 over 1 bar, 2 sub 1 over m, and here I have 2 over m. And the 2 doesn't imply there isn't a screw axis anywhere coming out at me. It just says that there's at least a twofold axis. And if there is a screw axis, it's just in there besides that. Because if I have a choice of 2 versus 2, 1, the convention says I should only show the 2. So that's one of the problems here. Although if you were to fill this out and say I have a centered lattice, I'm putting in twofold axis, and I'm putting in a perpendicular horizontal mirror plane, I would generate all of the other symmetry elements, and that's why this notation is used that way. Here you can see a notation that suggests that I have a twofold axis coming out at me, and I have a perpendicular plane. Actually, I don't have a perpendicular mirror plane, but I have a perpendicular glide plane. And then over here, I see that I have screw axes, and note that when I go up in my axes symmetry, so for example, over here, I have twofold axes, but I only see a screw axis 2 sub 1. I don't see anything else. Where when I come up here and I have a fourfold axis, I can have 4 sub 1, 4 sub 2, 4 sub 3, which suggests that as I go to higher symmetry rotational axes, my options in terms of the number of screw axes increases. So we'll want to discuss that, and we will. And you can see that, of course, if I go further, because if I look at the sixfold, when I start to put in right here, when I put in a sixfold axis, you can see here I can go up to 6, 5. And what's interesting is that as you go to more higher symmetries, it's hard to see those options, and that is likely that there's so many other symmetry elements that dominate the notation. There are screw axes probably in here, but you don't see them. And that's it. So with that quick overview of the 230 point groups, let's go and derive some missing elements like screw axes. We'll discuss them, talk about some notation, and then in the last lecture, a couple lectures from now, we will finish with just going through some images from international databases, and then you should have all the ammo to understand the 230 point groups, space groups.